Good afternoon. Design of beams and shaft. In this chapter, we will discuss how to design a beam so that it is able to resist bending and shear. Specifically, methods used for designing prismatic beam and determining the shape of fully stressed beam will be developed. At the end of the chapter, we will consider the design of shafts based on the resistance of both bending and torsional moments. The basics of the beam design. The beams are said to be designed on the basis of strength so that they can resist the internal shear and moment developed along their length. To design a beam in this way requires application of a shear and flexural formulas, provided the material is homogeneous and has linear elastic behavior. Although some beams may also be subjected to an axial force, the effect of this force are often neglected in design since the axial stress is generally much smaller than stress developed by shear and bending. As shown in the figure, the external loading on the beam will create additional stresses in the beam directly under the load. Notably, a compressive stress will be developed in addition to the bending stress and shear stress. Using advanced method of analysis as treated in the theory of elasticity, it can be shown that sigma y diminishes rapidly throughout the beam depth. For most beam span to depth ratio used in engineering practice, the maximum value of sigma y generally represents only a small percentage compared to the bending stress. Furthermore, the direct application of concentrated load is generally avoided in beam engine. Instead, the bearing plates are used to spread these loads more evenly onto the surface of the beam. Although the beam are designed mainly for strength, they must also be braced properly along the sides so that they do not buckle or suddenly become unstable. Furthermore, in this case, the beams must be designed to resist limited amount of deflection, as when they support ceiling made up of brittle material such as plaster, limitations placed on the beam buckling are often discussed in code related to structural or mechanical design. Since the shear and fractional formulas are used for beam design, we will discuss the general results obtained when these equations are applied to various points in a cantilevered beam that has a rectangular cross section and supports a load at its end. In general, at an arbitrary section along the beam axis, the internal shear and moment are developed to form a parabolic shear distribution and linear normal stress distribution. As a result, the stress acting on the elements located at point 1 through 5 along the section is also shown in the figure. In case, the state of stress can be transformed into principal stresses using either the stress transformation equation or the Morse circle. The results are shown in figure. Here, each successive element undergoes a counterclockwise orientation specifically relative to element considered to be at 0 degree position. Element 3 is considered and oriented at 90 degree. So here one example, it is a simply supported beam, but it have the two different supports. One is point support, otherwise called as a knife edge, and another point at B, which have the roller support. Here we are giving the two different concentrated loads. So initially, how to solve this type of problem is, initially we have to find out the reaction that take place at both the end, at A and B. So first initially we have to take the reaction. So we have to consider as sigma mb equal to 0. So by using these relations, we are going to find out so what will be the corresponding reaction at RA and RB. So after that, what we are going to do is we are going to calculate that force at a particular point from right hand side or else left hand side. So in this case, we having instead of an point load, we having a UDL load, and these are the solution for that problem. Thank you.